So previously I just digressed about this distribution because I don't want to lose the flow of the lecture. Let's review about why this one follows T distribution and why it is F distribution. So for whatever reason, suppose for whatever reason, actually we have two regions. Based on two reasons, we can assume that beta hat follows normal distribution, right? We can either assume epsilon is normal distribution, or we can assume that we have a large number of data. Okay? But anyway, okay, we know this one, right? And then in the previously, which example I wanna use? Suppose let's use wild test. The wild test. If our null hypothesis is right, if HO is right, okay, then okay, C beta hat. Actually, this one should over here. So C beta and then C prime sorry, right? It should be like this, right? And if null hypothesis is right, then this one should be, and C beta is B, so B right? Do you follow up to this part? Where is wild test? Actually, sorry. We to make a notation consistent, prime over here, and prime over here. Okay. So beta hat follows the normal distribution with mean beta and sigma square x prime x inverse. And if we multiply C prime in front of the beta hat, then we are simply multiplying basically constant vector. So it should be normal distribution with C, with normal distribution C prime B, and a sigma square C prime x inverse C, right? We all know this one. This holds because either large sample or assumption, and then because of C is constant, we have this one. And if our null hypothesis is right, this one should follow this one, right? Because if null hypothesis is right, C prime beta is B, right, in wild test. Therefore, okay, from this one, okay, in the using this normalization property, okay, this one. This normalization we have, okay, we have C beta hat minus B divided by sigma root C prime x inverse C should follow what? Should follow normal distribution with mean 0, and then I, right? I, and here it is actually 1. This should be simply 1 because we have only actually it is k. If we have a k number of okay, we have a complicated wild test and simple one. So for general wild test, where is it? No, not this one. Okay. So in this case we have only one restriction, so k is 1. But suppose we have more than one restriction, then in this more general world test, this is we have k, this is b is k, right? Vector with length is k, so basically it's ik, right? But anyway, for simplicity, okay, suppose we have only one restriction, like your homework, if you have only one restriction, okay, then this should follow normal distribution, right? So if we know, okay, we can calculate this one, well, simple regression, and we know p, it is from our hypothesis. C is again given from our hypothesis, and x prime x inverse is we can calculate and see, but this is something we don't know, right? This is something we don't know. But suppose we know this one, sigma. If we know this sigma, and then if we calculate this one, then we can use this one as a statistic, and we can do the hypothesis testing, right? We can calculate, if we know this sigma, then we can calculate this one. And then from standard normal distribution, okay? And so suppose this is 2 minus 2 and 2, okay? And suppose, let's say this value is z hat. And what we can do as we do usually, if z hat is between this area, okay, we cannot reject the null hypothesis, okay? But if z is either this one or this one, then we reject null hypothesis of this one, right? Okay, this is clear until now, right? But problem is that we don't know this one, right? Probably we don't know this one. So alternatively, what we can do is we have to use here number of what is world test. Okay, here it is n. Okay, n plus 1 number of variables. Okay, so in our example, number of the variables is n plus 1, right, including constant. We have small n. So what we instead do is we calculate sigma square. Okay, sigma square is basically t minus 1 plus n, and then square. Okay, we have something like this one. Okay, and then next, what we want to do is, okay, actually this is regression error, so it is different from epsilon, but we know epsilon is 0 plus sigma square, right? Square. So what you know is that epsilon over sigma should follow normal distribution 0, 1. Okay. But problem is that, of course, epsilon hat is different from epsilon, but let's disregard that difference for the time being. Then what we wanna do is we divide s square with sigma square. Okay, and then what we have here is t minus 1 plus n, and then summation of epsilon hat I over sigma, right, square. Okay, we have something like this. And then since each epsilon, okay, again epsilon hat and epsilon is slightly different, but since each epsilon is normal distribution, okay, normal distribution, and then if we divide epsilon with sigma, then it follows standard normal distribution. And if we add this one, this is standard distribution from 1 to t, right? So it is like a summation of a square of the standard distribution, right? So this one should follow this part. This part is, okay, this part is like summation of the normal distribution. Right? Summation of normal distribution. So this part follow chi-square distribution. Okay, chi-square distribution. But problem is that this epsilon hat is different from this epsilon. Right? How different? This epsilon is population property, but this epsilon hat is regression error of using 1 plus n information, right? So therefore, instead of this one have degree of freedom, right? We add from 1 to t. So our initial guess is that this one has a degree of freedom t, but this one does not have a degree of freedom t. Instead, it has degree of freedom 1 plus n, because we use 1 plus n variable already. We use that information already to estimate epsilon's hat, right? So this part, okay, this part follows chi-square distribution with degree of freedom t minus 1 plus n, right? So, okay, what we can do is, therefore, what we can do is, let's call this one is, okay, let's call this part like this one. So, what we can do is, from beta minus b, okay, sigma root c, and then what we wanna do is, okay, we divide this one with, okay, we divide with this one, okay, and then we divide this one again by 1, right? Divide this one. Okay, then what we have is it is a normal distribution, and we divide with chi-square distribution, and divide that chi-square distribution again with the degree of freedom. Then we have something like, oh sorry, we need a root. Okay, we divide this one, then we have a t distribution, right? Now we have a t distribution, but conveniently, okay, still we don't know this one, but conveniently, this one, and here it is again, this entire part is actually s sigma square multiplied by root t minus 1 plus n. Actually, it is a root, so this one goes away. So actually, this one and this one cancels each other. Okay, cancels each other. And inside of S, again we have this part. So this one and this one again cancels out. Okay, everything cancels out. So this entire part becomes C prime beta minus B over S now. C prime X C, inverse C, right? You get it? So I mean, in order to prevent the digression in the class, I simply change sigma to S and change this G normal distribution into the T distribution. But when I change sigma to S, what I implicitly did is actually this operation. Okay. In the end, they cancel each out. Everything cancels each other. So only sigma becomes the S. Right? So this one follows now T distribution with degree of freedom T minus n plus 1. And then, since we don't use sigma and instead we use S, now we know everything. So we can do hypothesis testing. Okay? Okay, any question? No? It should be easy, right? Okay.
In this video, I want to talk about what is easily one of the most fundamental and profound concepts in statistics, and maybe in all of mathematics, and that's the central limit theorem. Central limit theorem. And what it tells us is we can start off with any distribution that has a well-defined mean and variance, and if it has a well-defined variance, it has a well-defined standard deviation. And it could be a continuous distribution or a discrete one. I'll draw a discrete one just because it's easier to imagine, at least for the purposes of this video. So let's say I have a discrete probability distribution function. And I want to be very careful not to make it look anything close to a normal distribution, because I want to show you the power of the central limit theorem. So let's say I have a distribution. Let's say it can take on values 1 through 6. 1, 2, 3, 4, 5, 6. It's some kind of crazy dice that's very likely to get a 1. Let's say it's impossible. Let me make that a straight line. You're very high likelihood of getting a 1. Let's say it's impossible to get a 2. Let's say it's an okay likelihood of getting a 3 or a 4. Let's say it's impossible to get a 5. And let's say it's very likely to get a 6 like that. So that's my probability distribution function. If I were to draw a mean, this is symmetric, so maybe the mean would be something like that. The mean would be halfway, so that would be my mean right there. The standard deviation, maybe it'd be that far and that far above and below the mean. But that's my discrete probability distribution function. Now what I'm going to do here, instead of just taking samples of this random variable that's described by this probability distribution function, I'm going to take samples of it, but I'm going to average the samples and then look at those samples and see the frequency of the averages that I get. And when I say average, I mean the mean. So let's say, let me define something. Let's say my sample size, and I could put any number here, but let's say first off we try a sample size of n is equal to 4. And what that means is I'm going to take 4 samples from this. So let's say the first time I take 4 samples, so my sample size is 4. Let's say I get a 1, let's say I get another 1, and let's say I get a 3, and I get a 6. So that right there is my first sample of sample size 4. And I know the terminology can get confusing because this is a sample that's made up of 4 samples. But when we talk about the sample mean and the sampling distribution of the sample mean, which we're going to talk more and more about over the next few videos, normally the sample refers to the set of samples from your distribution, and the sample size tells you how many you actually took from your distribution. But the terminology can be very confusing because you could easily view one of these as a sample. But we're taking 4 samples from here. We have a sample size of 4. And what I'm going to do is I'm going to average them. So let's say the mean, I want to be very careful when I say average, the mean of this first sample of size 4 is what? 1 plus 1 is 2. 2 plus 3 is 5. 5 plus 6 is 11. 11 divided by 4 is what? 2.75. 2.75. That is my first sample mean for my first sample of size 4. Let me do another one. My second sample of size 4. Let's say that I get a 3, 4, let's say I get another 3, and let's say I get a 1. I just didn't happen to get a 6 that time. And notice, I can't get a 2 or a 5. It's impossible for this distribution. The chance of getting a 2 or 5 is 0, so I can't have any 2s or 5s over here. So for this second sample of sample size 4, my sample mean for my second sample mean is going to be 3 plus 4 is 7. 7 plus 3 is 10. Plus 1 is 11. 11 divided by 4, once again, is 2.75. Let me do one more because I really want to make it clear what we're doing here. So I do one more. Actually, we're going to do a gazillion more, but let me just do one more in detail. So let's say my third sample of sample size 4. So I'm going to literally take 4 samples. So my sample is made up of 4 samples from this original crazy distribution. Let's say I get a 1, and a 6, and a 6. And so my third sample mean is going to be 1 plus 1 is 2. 2 plus 6 is 8. 8 plus 6 is 14. 14 divided by 4. 14 divided by 4 is what? 3 and a half. 3 and a half. And as I find each of these sample means, so for each of my samples of sample size 4, I figure out a mean. And as I do each of them, I'm going to plot it on a frequency distribution. And this is all going to amaze you in a few seconds. So I plot this all on a frequency distribution. So I say, okay, on my first sample mean was 2.75. So I'm plotting the actual frequency of the sample means I get for each sample. So 2.75, I got it one time, so I'll put a little plot there. So that's from that one right there. And I got the next time, I also got a 2.75. That's a 2.75 there, so I got it twice. So I'll plot the frequency right there. Then I got a 3.5. So all the possible values, I could have a 3, I could have a 3.25, I could have a 3.5. So then I had the 3.5, so I'll plot it right there. And what I'm going to do is I'm going to keep taking these samples. Maybe I'll take 10,000 of them. So I'm going to keep taking these samples. So I go all the way to 10,000. I just do a bunch of these. And what's going to look like over time is each of these, I'm going to make it at a dot because I'm going to have to zoom out So if I look at it like this, over time, still has all the values that it might be able to take on. 2.75 might be here. So this first dot is going to be, this one right here is going to be right there. And that second one is going to be right there. Then that one at 3.5 is going to look right there. But I'm going to do it 10,000 times because I'm going to have 10,000 dots. And let's say as I do it, I'm going to just keep plotting them. I'm just going to keep plotting the frequencies. I'm just going to keep plotting them over and over and over again. And what you're going to see is, as I take many, many samples of size 4, I'm going to have something that's going to start kind of approximating a normal distribution. So each of these dots represent an incidence of a sample mean. So as I keep adding on this column right here, that means I kept getting the sample mean 2.75. So over time, I'm going to have something that's starting to approximate a normal distribution. And that is the neat thing about the central limit theorem. So the central limit, and this was the case for, so in orange, that's the case for n is equal to 4. This was for sample size of 4. Now, if I did the same thing with a sample size of maybe 20. So in this case, instead of just taking 4 samples from my original crazy distribution, every sample, I take 20 instances of my random variable, and I average those 20, and then I plot the sample mean on here. So in that case, I'm going to have a distribution that looks like this. And we'll discuss this in more videos. But it turns out if I were to plot the sample, 10,000 of the sample means here, I'm going to have something that, two things. It's going to even more closely approximate a normal distribution. And we're going to see in future videos, it's actually going to have a smaller, well, let me be clear. It's going to have the same mean. So if that's the mean, this is going to have the same mean. But it's going to have a smaller standard deviation. So I should plot these from the bottom because you kind of stack it. One you get one, then another instance, and another instance. But this is going to more and more approach a normal distribution. So the reality is, and this is what's super cool about the central limit theorem, as your sample size becomes larger, or you can even say as it approaches infinity, but you really don't have to get that close to infinity to really get close to a normal distribution. Even if you have a sample size of 10 or 20, you're already getting very close to a normal distribution. In fact, about as good an approximation as we see in our everyday life. But what's cool is we can start with some crazy distribution. Right? This has nothing to do with a normal distribution. But if we have a sample size, this was n equals 4, but if we have a sample size of n equals 10 or n equals 100, and we were to take 100 of these instead of 4 here and average them and then plot that average, the frequency of it, then we would take 100 again, average them, take the mean, plot that again. And if we were to do that a bunch of times, in fact, if we were to do that an infinite time, we would find that especially if we had an infinite sample size, we would find a perfect normal distribution. That's the crazy thing. And it doesn't apply just to taking the sample mean. Here we took the sample mean every time, but you could have also taken the sample sum. The central limit theorem would have still applied. But that's what's so super useful about it. Because in life, there's all sorts of processes out there, proteins bumping into each other, people doing crazy things, humans interacting in weird ways, and you don't know the probability distribution functions for any of those things. But what the central limit theorem tells us is that if we add a bunch of those actions together, assuming that they all have the same distribution, or if we were to take the mean of all of those actions together, and if we were to plot the frequency of those means, we do get a normal distribution. And that's frankly why the normal distribution shows up so much in statistics, and why, frankly, it's a very good approximation for the sum or the means of a lot of processes. Normal distribution. What I'm going to show you in the next video is I'm actually showing you that this is a reality, that as you increase your sample size, as you increase your n, and as you take a lot of sample means, you're going to have a frequency.
To central limit theorem means that, classical central limit theorem. Let x1, xn be a random sample of size n. That is a sequence of independent and identically distributed random variables drawn from this expected value. Then sample average looks like this. And then by the large number of central limit composition probability almost surely to mu s. And then classical theorem describes the size and distribution form of the 왜 이렇게 말이 길지? I think this is better. Lindbergh-Levy classical central limit theorem. Suppose x1, xn be a sequence of IID random variable with mu and sigma square. So central limit theorem may not hold. okay, if variance, if this does not exist or variance is infinity. But at least x are drawn from some distribution that has mean and variance, then this one converges to normal distribution. Okay, this is basically average. Okay, sample average converges to some normal distribution. Okay, that's the property. So okay, this one is very similar to in our example. Yes, this one. Okay, so in this case, again, we don't know what is going on beta, right? We don't know nothing about beta. Okay, we know nothing about beta, but actually, we don't know anything about beta hat. Okay, okay, we don't know anything about beta hat, but at least from the asymptotics, if we have large numbers, at least we know beta hat converges to beta, and beta hat and variance covariance matrix beta hat minus beta, this one converges to something like this one. Okay, then by a central limit theorem, okay, beta hat is basically looks like a sample average in some sense. Beta hat is very similar to sample average anyway. So that sample average minus beta, this one will converge to normal distribution. Okay. So anyway, that's the property. Okay. So here, actually, beta hat. Let me be more clear. Actually, beta hat minus beta looks like average, because beta hat minus beta is something, it is stable, and this one divided by t, right? So this one is something similar to some sort of average. Okay, this one looks like average, and we know this one likes this. So therefore, in the Wikipedia definition, root n sample size n sample average minus mu converges to sigma square, and we know sigma square, so this one converges to this one. Okay. Now I think we are ready to go to next topic. Next topic is until now we focused on ordinary least squares method, and now we want to generalize that one. Okay, generalized least square. Okay. Okay, so this is our original model. So our specific y equal x beta plus epsilon, we are assuming linear model. And then expectation of epsilon is 0. And we assume x and epsilon are independent of each other. Okay, x doesn't include any information about epsilon, and epsilon does not include any information about x. Okay, and then this assumption. Okay, these epsilon terms, these error terms are independently and identically distributed. So it is a variance covariance matrix of epsilon is sigma square multiplied by I. Okay, and now we want to relax this assumption. Okay, so instead of this assumption, okay, we consider relaxing assumption 4. So instead we assume that now expectation of epsilon, epsilon hat, epsilon prime becomes some matrix, some T by T matrix. So we want to generalize. Okay? Our question is what's going to happen if we don't have this simple assumption anymore? Oh, don't worry, it is not that difficult. Anyway, in this section, we consider that one. And then, of course, this omega matrix is symmetric and positive definite matrix. Okay? It is symmetric because it is variance covariance matrix, and it is again positive semi-definite matrix because it is again variance covariance matrix. Okay? And then, if we assume epsilon follows normal distribution, okay? This is, I think, something you have to memorize. Now, okay, in the previous example, epsilon follows normal distribution with 0 sigma square I, okay? And now, okay, we are assuming that now we are assuming that epsilon follows normal distribution 0 and omega. Okay. If epsilon follows normal distribution, multivariate normal distribution with mean 0 and variance covariance matrix omega, then the probability density function 확률 밀도함수 for epsilon looks like this. Actually, in this case, it's y. Okay. Anyway, y minus x beta is epsilon, so okay. Yeah. 매트릭스 T by T 매트릭스. variance covariance 매트릭스라고 해요. 예? 어디에 분산으로 들어가냐고? 아니 이제까지 그거 아니 이거 똑같은 거지. 그렇죠? 베타 햇도 그렇죠? 이거 생각 안 나나 이거? 이것도 매트릭스였잖아. 그러니까 이게 뭐냐면 이게 여기서는 엡실론이 변수 숫자가 몇 개지? 여기서는 데이터 숫자가 t라면 오케이. 이거는 t 곱하기 1 매트릭스고 이건 t 곱하기 t 매트릭스고 이건 t 곱하기 1 매트릭스고 그래서 이 매트릭스의 다이거널 텀들은 그러니까 이 오메가 매트릭스의 다이거널 텀들은 이 엡실론 하나하나의 베리언스 거고 업다이거널 텀들은 엡실론끼리의 코베리언스인 거죠. 그렇죠? 그래서 베리언스 코베리언스 매트릭스라고 하는 거예요. 네. 또 다른 질문. 네. So this is a likelihood function or probability density function. It depends on perspective anyway. So in this case, it is a probability density function for y, in which mean is x beta, and variance covariance matrix is omega. Okay. And then we want that this one should be okay, always greater than equal to 0. That should be so that density does not explode. This one is, I mean, in the univariate distribution, this term, okay. This one is anyway something similar to this one, right? Something similar to that one is something similar to, right? That is something similar to this one, and we know this one is always positive. This one should be always positive, and in the multivariate version, okay. This one, that one is multivariate version of this one, and again, we want that is positive always. Okay. Now consider a covariance matrix omega of a random vector epsilon with its mean is 0. That is not positive semi-definite matrix. Then we have a problem. Okay. So okay, let me provide the more intuitive for positive semi-definite. Consider a covariance of random vector epsilon that is not positive semi-definite Okay. If you remember the definition of a positive semi-definite matrix, if omega is not positive semi-definite matrix, then there exists some vector c such that c prime omega c is less than 0. Okay. Now consider the linear combination of c epsilon. Okay. Suppose we want to investigate c prime epsilon. Note that c prime epsilon is always scalar, right? It is scalar. So variance of the c prime epsilon, it is just a number. Okay. Variance c prime epsilon is expectation of c prime epsilon epsilon prime c. That is again c prime expectation epsilon epsilon prime c, and we know expectation of epsilon epsilon prime is omega. So c prime omega prime c, but omega prime is the same to omega. Okay, and this is less than 0. And so it does not make sense. Or variance shouldn't be, okay. It is possibly 0, but we know epsilon is not constant. Okay, not constant. Therefore, this one should be always positive. Right? It is a basically variance of some random number, right? So this one should be always positive. So if omega is not positive semi-definite matrix, it means that we have some linear combination of variables so that we can make this variance non-positive, which does not make sense, which is not possible. Right? So therefore, omega should be always positive definite. And there should be which means that for every c, for all c, this one should be always positive. I think you are confused, so to refresh your memory, linear algebra, where is linear algebra? Matrix algebra, I think we learned that one. In the matrix algebra, okay, yeah. Right. In the matrix we learned positive semi-positive definiteness, right? And positive definiteness, okay. Positive definiteness means consider square matrix X A, and A is positive definite if for all X prime AX is positive, and X is called positive semi-definite if for all X not equal to 0, X prime AX is greater than equal to 0. If there is some X, there exists a X such that A is X. A can be represented as X prime X, then A should become positive semi-definite. And if there exists some X such that A becomes X prime X with N is greater than equal to M, and rank X is M, i.e. all of the column of X are linearly independent, then A is positive semi-definite. If all of the alternatively, if all of the eigenvalues of A are positive, then again A is positive definite, and if all of the eigenvalues of A are non-negative, then A is positive semi-definite. Okay. And for negative definite matrix and negative semi-definite matrix, we have a comparable definition. Okay. Now consider, for example, consider a special case such that t is equal to 2. Okay, so in this case, observation is 2. So in this case, suppose this is our assumption. Suppose omega matrix looks like sigma 1 square, rho sigma 1, sigma 2, rho sigma 1, sigma 2, and sigma 2 square. Suppose our matrix looks like this. Variance covariance matrix looks like this. And then in order for omega matrix positive semi-definite matrix, then first diagonal term should be always positive. Sigma 1 square should be greater than or equal to 0, and sigma 2 should be greater than or equal to 0. Okay. Then sigma 1 square, sigma 2 square minus rho square, sigma 1 square, sigma 2 square should be greater than 0. And sigma 1 square, sigma 2 square, 1 minus rho square should be equal to, should be greater than 0, which means that rho should be less than 1. Okay. In this case, as you can see, rho is the correlation. Okay, rho is simply correlation between two random variables. And as you know, correlation, that absolute value of the correlation is always between minus and 1, minus and 1 and 1, right? So it means that as far as it is a covariance matrix of the two random variables, okay, then that covariance matrix is always positive definite. Right? Now, suppose, let's go to the next example. Suppose y is x beta plus epsilon. Okay, this looks same to our previous linear model, but we have additional complications. Okay, now additional complication is that now there is some relation between error terms. So suppose epsilon t is rho epsilon t minus 1 plus et. And now suppose et is IID and mean 0 and sigma e squared. Right? Now our error terms is more complicated, right? In the previous case, we have simply, in our previous OLS examples, simply rho is simply 0, right? But now, error term of the previous sample affect today's error term. No. Error term of the previous sample affect error term of this sample. If we interpret t as a time in your homework, for example, it means that yesterday's shock to the model affects today's shock also. Okay, something like that. And then first, okay, first, epsilon expectation of epsilon t is 0. Okay, why? Because if we put expectation over here, the expectation of epsilon et and this is expected et, and expected epsilon t is epsilon same to expectation of epsilon t minus 1. So it is 1 minus lambda expectation of epsilon t, and it is same to expectation of et. But expectation of et is 0. So expectation of epsilon t should be 0 too. Okay. Independently and identically distributed. So it means that this ET, for each ET is independent of each other, and each ET has exactly same distribution, looks like this. So I'm kind of disorganized with the blackboard, but epsilon t equals rho epsilon t minus 1 plus et. And if we put expectation over here, it is expectation over epsilon t equals rho expectation over epsilon t minus 1 plus expectation over et. Right? But this one and this one, okay, we can put together. T, basically, because, okay, and because it is an unconditional expectation, so basically subtract t does not matter. Okay, so we can simply drop t. But since this is 0, okay, and then therefore this one should be 0 too. Now next, let's calculate variance of the unconditional variance. Okay, mean of epsilon t is 0, so expectation of epsilon square should be the variance of epsilon t. Okay, unconditional variance of epsilon t, which let's call it sigma epsilon square, and this is expectation of rho epsilon t minus 1 plus et square. Okay, and then we can expand the square term. Then we have expectation of rho square epsilon square t minus 1 plus e rho epsilon t minus 1 e t minus 1 plus e t square. Right? And now we can put expectation inside. Okay? So if we put expectation inside, this is the simply epsilon square. First term is expectation rho square of epsilon t minus 1 square. So expectation of epsilon t minus 1 square is the same to expectation epsilon t square. Okay, we can drop t because it's unconditional. So we can write the first part as rho square and sigma epsilon square, right? And the second term goes away, right? Because expectation of et is 0, and at time t, okay, at time t, since epsilon t minus 1 is already given, okay, and et and epsilon t minus 1 are independent of each other, okay. Actually, then independent is not necessary, but it does not matter. So independent, so the second term go away, and about third term, expectation of et square is given as sigma e square, right? So eventually, expectation of epsilon t square becomes rho square sigma epsilon square plus sigma e square. But again, we defined expectation of epsilon t square as a sigma epsilon square, right? So it means that sigma epsilon square equal to rho square sigma epsilon square plus sigma e square, right? But thus it means that if we solve this one, then it means that sigma epsilon square should be equal to sigma e square over 1 minus rho square. Okay? So we should have this relationship. And likewise, expectation of epsilon t and epsilon t minus 1, the covariance between those two. Again, I mean, mean of the epsilon t and the mean of the epsilon t minus 1 is all 0, right? So expectation of epsilon t and epsilon t minus 2 is covariance between the epsilon t and epsilon t minus 2, right? So anyways, the covariance between epsilon t and epsilon t minus 2 is expectation of rho epsilon t minus 1 plus et and epsilon t minus 2. This is equal to expectation of rho of epsilon t minus 1, epsilon t minus 2 plus et epsilon t minus 2, right? And then again, we know epsilon t minus 1. Since epsilon t minus 1 is the same to rho epsilon t minus 2 plus et minus 1, we can plug that one. So we have expectation of rho parentheses rho epsilon t minus 2 et minus 1 and epsilon t minus 2 plus et epsilon t minus 2. Right? And from this, we can put expectation inside. If we put expectation inside, then this part is 0. Okay? And oh no, we have multiplied this part. So if we put expectation inside, it is rho square. This part is rho square and sigma square. And the second part is 0, third part is 0. Right? So eventually, what we should have is rho square sigma epsilon square. And then this one is, since sigma epsilon square, we know sigma epsilon square, sigma epsilon square looks like this. So we plug this one, so we have this relationship. Okay. Actually, I skipped this one. My mistake, but anyway, I think it is clear. So, I mean, we can find the pattern, right? Epsilon et square is sigma epsilon square, which is 1 minus rho square over abnormal. Sigma e square over 1 minus rho square. And if we calculate covariance between the shock between one period ago, t minus 1, now we have correlation term about here. And if we calculate covariance with 2 period ago, t and t minus 2, now we have rho square, right? Rho square. So if we can continue this one, then what it means is that covariance between epsilon t and epsilon t minus k should be rho k sigma e square over 1 minus rho square, right? And then so we entirely characterize the omega matrix, and omega matrix should be look like this. Okay. Omega matrix is this diagonal terms are all sigma epsilon square, and we know sigma epsilon square should be sigma e square over 1 minus rho square. And up diagonal term is basically covariance between t and some sort of t minus k terms. Right? And they are all multiplication of rho k to the variance of sigma epsilon square. Right? So omega matrix should be look like this. And we have a special name for this kind of variance covariance matrix, and this structure is called autoregressive of order 1, or simply AR1 model. Okay? So again, this type of model is called AR1 model. AR1 model is, it has its name because, clearly, epsilon has correlation with itself, right? It has correlation with itself, but 1 day ago, 1 period ago. So that's why we call it autoregressive model. And it is autoregressive model with degree of 1 because it has autoregressive, autocorrelation relation with just 1 day ago, not 2 or 3 days ago. Okay? It's just 1 day ago, 1 period ago. So that's why we correlate this one as autocorrelation with just 1 period ago, so we call it AR1 model. If it has like correlation term like epsilon t minus 2, which means that epsilon t has correlation or covariance with 2 period ago, then we call this kind of model with AR2 model, autocorrelation with degree 2. 그렇지. 예, 공분사의 정의. 그러니까 이게 베리언스 코베리언스 매트릭스인 거지. 그러니까 두 개의 랜덤 베리어블 간의 베리언스 코베리언스 매트릭스를 구한 거잖아. 그렇죠? 그래서 이거에 적어줘. epsilon 1과 epsilon 2 간의 베리언스를 구했더니 그런 거 아니야. 이거 아니야. 이것들이 물론 민이 지로라면 민이 지로라고 하지 말고 이거면 당연히 이렇게 생긴 거 아니에요. V epsilon 1, V epsilon 2 and covariance epsilon 1, 2 and covariance epsilon 2, epsilon 1 이렇게 된 거지. 예. 근데 우리가 여기서 보면 편하게 그렇죠? 이걸 그냥 시그마 1 스퀘어로 표시하고 이걸 시그마 1, 2 스퀘어로 표시하고 얘는 시그마 1, 2인데 그렇죠? 이걸 롤을 이용해서 표현을 해준 거죠. 그래서 이런 것들이 그러니까 베리언스 말하고 하냐면 뭐냐면 베리언스 코베리언스 매트릭스 반드시 파저티브 데피니트 하다는 거지. 그렇죠? 이 매트릭스가 파저티브 데피니트 하려면 그렇죠? 이 다이어고널 텀들이 0보다 크고 이 행렬의 그렇죠? 행렬식이 0보다 커야 된다는 건데 행렬식이 0보다 커야 된다는 거지. 행렬식이 0보다 크다는 말은 뭐냐면 로가 1보다 작다는 말이고 그렇죠? 로가 1보다 작다는 말이고 그 말은 얘와 얘가 퍼펙트 코릴레이션 아닌 이상 사실상 똑같은 애가 아니면 로는 1보다 작아야 되니까 그렇죠? 사실상 똑같은 애들이 아닌 것끼리 코베리언스 코베리언스 매트릭스 구하면 그 베리언스 코베리언스 매트릭스는 반드시 파저티브 데피니트하다는 거죠.